In previous videos, we looked at two approaches as far as limits are concerned. We looked at the numerical approach, where we used a table to kind of investigate or get a conjecture about the value of a limit. We also looked at a graphical approach as far as what if you're given the graph of a function? How can you determine certain limits based on that graph? What we're going to do in this video is we're going to look at some algebraic properties of limits. And, the concept of algebraic properties shouldn't be foreign to you because you've seen like algebraic properties of numbers, of functions, and now we're going to add that of limits to this list, right? So I'm going to take a few minutes and state the properties and then just do a couple examples to show you how they are used, right? So this is a theorem, right? But with as the case for most of the theorems that involve limits, we will forego doing a formal proof simply because the formal proof requires a bit more formality, which we don't cover in this level of calculus. So let's say this. So suppose these two limits exist. The limit as x approaches a of f of x is equal to, let's call it big L for limit, and also that the limit as x approaches a of g of x. Now, I can't use the same letter L, right? And unfortunately, we'll have to use a different letter. I'm going to use an uppercase M. So suppose both of these limits exist, right? So we know that this function, the function values in both directions, because this is a two-sided limit, the function approaches a value of L as x gets closer and closer to a. The x doesn't have to actually get to a, and the function value, the y value, doesn't necessarily have to get to L in order for this statement to be true, right? It's a lot different from saying f of a and so forth, right? So these properties will tell us what to do, or what the result would be is if we were to somehow combine these two functions and then take the limit, right? So in other words, if you do some algebra with the functions f and g and then have to compute the limit, well, we can make use of these known facts, right? So I'm going to state the conclusions, and I'll number them as we go. So then, what can we conclude? Well, one of the simplest ways to take two separate functions and combine them to make one is to add or subtract, right? So what if, again, let me do it in this order. What if we were to take f of x and then either add or subtract g of x, and then compute the limit of the sum or difference? So what if we did this, right? So this notation here is basically saying, what is the limit of the sum or difference of these two functions as x approaches a? Well, what the property says in terms of addition and subtraction, you could do this. You could take, provided you know that the limits that I'm about to write down exist, you can take the limit as x approaches a of f of x and either add or subtract the limit as x approaches a of g of x. So if these two limits exist and you're trying to find the limit of either the sum or the difference, what you can do is either find the sum or difference of L and M. So L plus or minus M, right? So it seems kind of logical. So let me say it this way. Let's say it out in terms of addition. If F approaches L and G approaches M, then intuitively it makes sense that F plus G would approach L plus M. And similarly with the difference, right? So that one's pretty straightforward. Second property, well, what else could we do with these two functions f and g? Well, we could multiply them, right? So we could take the limit as x approaches a of f of x times g of x, right? Well, it turns out that the same kind of process holds. What you can do is you can take the limit, again, provided you know that these two things are exist, right? So this limit exists, and then times this limit, right? So this is basically saying the limit of the product is the product of the limits. Again, we have to know that they exist, and that's why we wrote this down, right? So then this would end up being L times M, right? So we have properties now for sum, difference, and product. Well, what else could we do? Well, if you think of all the arithmetic operations you could do, you could take a quotient. In other words, you could divide them. That's another way that you could take this function and this function, again, given to you separately. There's a way you could combine them to create a third function, and that is through division. So if you're taking the limit of f of x over g of x, it turns out you can take the limit of the numerator. So that's the limit as x approaches a of f of x, divide that by the limit x approaches a of g of x, and then you would say, well, it's L over M, and you think you'd be done. Well, we have to be careful, because in terms of real numbers, right, you can always add, you can always subtract, you can always multiply and get another real number, right? Division, not so much. It works almost every time except if you have a zero in the denominator. So what we can say, to call this a property, we have to say that this is true provided what's in the denominator is not zero. So provided m is not equal to zero, right? So these three properties are really useful, because when you think of how more complicated functions are built, a lot of them are built in terms of these arithmetic operations, the addition, subtraction, multiplication, and division. But it turns out there is another function, another operation that is special to functions. And we will see this operation again and again throughout further study, right? And let me write it like this. So this is our fourth one. Now suppose you had another function, I'm going to call it h, right? And suppose you took f of x and then plugged f of x into h, so something like this. And again, you might remember this notation, right? This operation where you have two functions, it's called the composition of h and f, right? So it's where you replace the variable in one function with an entirely different function or another function. And then the question is, what is the limit of this expression, right? Well, under certain conditions, right, which we will get into later on. But under certain conditions, since you know that f of x approaches L as x approaches A, so I'm going to write this in red. So under certain conditions, which will be made clearer later on. So in a sense, we're kind of putting the cart before the horse. But under certain conditions, what you are allowed to do is essentially pass the limit through h and then put it in front of the f of x in parentheses. So it looks like this, right? So it's the limit as x approaches a of f of x, like that, right? So that's kind of the mental step here. And since we know that f of x approaches L, what we can do is replace that whole expression inside the h by an L, right? And what I will say is provided h, or I'll say this, provided L is in the domain of h of x, right? So there are a couple things that we have to make sure, and again, we will clarify these conditions, right? And actually that will be done pretty soon in a subsequent video. But under certain conditions, basically what this property is saying, if you can perform the operations that are defined by h of x, that function, right, with the limit of f, then that will be the limit of the composite, right? And yep, so those are the, well, I've listed them as 4 algebraic properties. You know, textbooks and other videos, they might do these separately, or they might kind of expand a little bit here with the composite, and maybe do it first with powers and then other kinds of functions. But here, as to keep this description as simple as possible, I'm just saying h represents a function that will satisfy certain conditions, and in examples that will be clear what we mean. And then once you can evaluate it at the number L, then that will be our answer. All right, so let's see how this plays out with a simple example. Right, so let's do an example. So what I'm going to do, suppose let me write it like this. All right, so suppose the limit as x approaches, in fact, yeah, let's not even do a, let's put a specific number there. So let's say 2 of f of x, let's say that's 5. And let's say we have another function. We have no idea what the function is. We just know that this function approaches a value, let's say -4. And let's do a third function. Now let's call this h of x. I might say, why am I using the h of x here? Well, again, you'll see why in a second. So let's say this is 1/2. So we have these 3 functions. The only thing we know about these functions is that as x gets closer and closer to 2, f of x, the y values for this function get closer and closer to 5. The y values for g of x get closer and closer to -4, and the y values for h of x get closer and closer to 1/2. Now let's go through and ask some questions that will require us to use one or more of these properties, right? So let's do part A. So let's compute the limit as x approaches 2 of, and let's say I have f of x plus 3 times g of x. All right. So again, what we have in square bracket would be considered another function. And the way that function is formed, it's by taking f of x and adding it to 3 times g of x. But because we don't know what, in other words, we don't know an equation for f and g, we're not given a graph for f and g, well, we can't use any of those methods, so we have to apply these algebraic properties. So let me apply the properties step by step so you can see what's going on. So the one with the addition tells us that I can split this up into two separate limits. So this is the limit as x approaches 2 of f of x plus the limit as x approaches 2 of 3 times g of x, right? Okay, so that's the property of the sum. We also have a property for multiplication, right? But in this case, the 3 is not another function. It's just a constant, and that makes it a little bit easier. Let me show you how it works for constants. So we have the limit as x approaches 2 of f of x. If we apply the property for the product, we have the limit as x approaches 2 of 3 times the limit as x approaches 2 of g of x, right? So this is our sum property and this is our product property. But because 3 is a constant, think of it when you think of the graph of a constant function, it is a horizontal line and it's always at the same y value. So we know that this limit is always going to be 3, right? So that would be my next step. And again, I'm showing the solution step by step and walking through the thought process so you can see how each step comes about. All right, and so in fact, if you want, let me kind of annotate this. So this is the sum property. This is the product property. And here, this is because 3 is a constant. So I'll just call that the constant property. And that's what we're using. Now, we could have applied all 3 of these properties at once and then just went from the original limit to this kind of broken down form. And now what we can do in this sort of broken down or stripped down form is use the information that's given. We're told that this limit is equal to 5. So this is 5 plus, and then we have 3 times. And then we're told that this limit is a -4. Right? And then to get our final answer, we go ahead and evaluate this expression. So we end up having 5 minus 12, which is -7, right? So this function, this f of x plus 3 times g of x, again, we don't know a lot about it. All we can say is that this function, as x approaches 2, that function approaches -7. Right? And again, it's because of these properties. Let's look at a second example here. So let's say we have the limit as x approaches 2, and I'll make this expression a little bit more complicated. Let's do like f of x times h of x all over the square root of h of x. Well, let's do like 8 times h of x minus g of x. All right. Okay, so this looks a little bit more complicated, So what we're doing, we have division, we have a product here, and we have another product here. One of the factors is a constant, that's an 8. We have a difference here, and then we have a square root. Now, I didn't specifically state a property for square roots, but that's where that composition comes in, because under the square root, we have this other expression, all right? Okay, so the first thing that we're able to do is to take the limit of the numerator like this separately, so I'll put that in parentheses there, and then take the limit of the denominator, which is that square root, right? So first, again, this is the property with the quotient, right, where you can take the limit of the numerator and the limit of the denominator separately. For the numerator, we can break it down even more. We can take the limit of the product. So the limit as x approaches 2 of f of x times the limit as x approaches 2 of h of x, right? So that's our product property. Now this is where we're going to use that property with the composition and take the limit inside the square root. So we're going to have a big thing here, and then this will be the square root of, well, what are we going to write down? So first we would have to take the limit of this product, which is similar to what we did in part A, and this will end up being 8 times the limit as x approaches 2 of h of x, and then minus, because it's a difference, and then the limit of g of x, right? So the limit as x approaches 2 of g of x. Now, let me highlight, or actually just kind of box off a couple things. These things that I'm boxing off are given to us. Right. In fact, we used 2 of them in part A. Right. So we know that f of x by itself as x approaches 2 approaches 5. H of x by itself, now that one we didn't do, but that was the 1/2. And same thing here, 1/2. And we know that g of x approaches -4. So what it boils down to, after looking at this complicated expression and then applying our limit properties, we end up with this expression. In the numerator, we have 5 times 1/2. In the denominator, we have a square root, but then we have some numbers to put under that root. So this is 8 times 1/2 minus -4, right? So after all is said and done, this is what we have. And again, just to emphasize, this is not a minus, this is a times, as is here, right? So let's simplify this and write this expression in its most reduced form. So the numerator is 5/2. We have, and I guess I'll go ahead and show these steps. So we got 4 for 8 times 1/2, and then I'm subtracting a -4, which is the same as adding 4. So we end up having a square root of 8 in the denominator, and we have a 5/2 in the numerator. That's certainly not in its lowest form, so what I'm going to do is this. So we have 5/2 divided by root 8, which is the same as 5/2 times 1 over root 8. Now I know that root 8 can be reduced further. That's 2 root 2. So I'll do this. So in the numerator I have 5. In the denominator I have 4 root 2. So we're pretty much there. But what I will say, you may have the tendency to rationalize this denominator, and if you do so, multiply the top and the bottom by root 2. And then what you end up having is 5 root 2 in the numerator, and then 4 times 2 in the denominator, which is 8. So we can say that this is our final answer in rationalized form, and that's the limit of this more complicated looking function, right? So a lot of the steps here aren't necessarily required. I mean, you could have left it as 5 over 4 root 2 unless you're prompted to rationalize the denominator. But more than anything, I'm just reminding you of all the different types of arithmetic or algebraic tricks or processes you can use in a problem like this, right? So hopefully these 2 examples will give you an idea of some of the algebraic things that you can do in computing limits, some of the properties that can be utilized, and then in a subsequent video we will dive either further into the algebra, and that's where you will really have to utilize things like long division or rationalizing or dealing with complicated fractions, right? And that's to come in a subsequent video. So hopefully this was informative and maybe even a little entertaining, and I will see you in a subsequent video.